No one sees it, no one photographs it, and no one realizes that the most dangerous part of any mega structure happens beneath the water. Hundreds of tons of steel and concrete rest on foundations built in complete darkness, under crushing pressure, where a single mistake can ruin entire projects. Engineers do not build underwater because it is impressive, they build underwater because without it, bridges collapse, tunnels fail, and cities stop moving. Water hides everything. Currents never stop, visibility drops to zero, and every meter deeper adds unimaginable pressure. Equipment corrodes faster, machines behave differently, and human limits are tested immediately. Yet bridges stand, tunnels survive, and foundations remain solid for decades because underwater engineering is planned with extreme caution. Long before construction begins, engineers study water behavior, river flow, seasonal changes, tides, storm patterns, and the chemistry of water itself. They drill test holes from floating platforms, extracting soil samples from meters beneath the surface to determine whether they are dealing with clay, sand, rock, or unstable sediment, because underwater construction cannot rely on assumptions. Mistakes remain invisible until it is too late, so these early surveys are critical. Every decision is calculated. Every choice of material, every pump, and every barrier is based on months or even years of planning. Three main methods dominate underwater construction: cofferdams, caissons, and diving systems. Each is chosen depending on water depth, soil stability, and current strength.
Floating massive structures
Cofferdams
like
are often the first solution.
Precise engineering,
a cofferdam is a temporary structure built inside water to create a dry working environment. Steel sheet piles are driven deep into the riverbed, interlocking tightly to resist water pressure. Once sealed, pumps remove the trapped water, slowly revealing wet soil and exposed ground while water continues flowing just outside the barrier. Engineers can now pour concrete, install reinforcement, and construct foundations safely. Cofferdams are commonly used for bridge piers, columns, and shallow foundations, but they have limits. Deep water increases pressure, strong currents can bend walls, and unstable soil can flood the site. Historical examples, such as the piers of the Golden Gate Bridge, relied heavily on cofferdams to stabilize the foundations in the fast-moving San Francisco Bay. Despite the technology of the 1930s, workers faced freezing currents and treacherous tides while installing steel sheets by hand, showing how difficult even shallow cofferdams can be. When cofferdams are impractical due to extreme depth or unstable soil, engineers turn to caissons. Caissons are massive hollow structures, often made of steel or concrete, that are lowered into water and gradually sunk into the ground. Some are open at the bottom, allowing soil to be excavated naturally, while others are sealed and pressurized. In pressurized caissons, compressed air keeps water out, creating an artificial atmosphere where workers can excavate soil beneath the structure. Entry and exit occur through airlocks, and internal pressure can be several times greater than normal, making breathing heavier and movement slower. Excavation continues until stable rock or soil is reached, and concrete is poured to form a foundation capable of supporting enormous loads. Workers must decompress slowly when leaving pressurized caissons to avoid decompression sickness, where nitrogen bubbles form in the bloodstream. Historical examples include the caissons used for the diving systems complement these methods for projects requiring direct underwater intervention. Construction divers wear heavy suits with helmets connected to surface air supplies, communication lines, and tethers for safety. Visibility is often zero, forcing divers to rely entirely on touch and memory. They install bolts, guide steel components, inspect welds, place formwork, and monitor concrete placement with extreme precision. Saturation diving allows divers to live in pressurized chambers for days or weeks, traveling to the worksite in pressurized bells and performing tasks with strict safety protocols. Machines, like remotely operated vehicles, now handle inspections, measurements, and some repairs without risking human lives, but human judgment remains irreplaceable. Engineers still need the subtle perception of vibration, resistance, and slight misalignments that machines cannot interpret. Underwater concrete is another challenge. Ordinary concrete cannot be poured underwater because it would wash away. Specialized mixes are used, resistant to separation and able to harden underwater. These are delivered through tremie pipes that extend to the bottom, allowing concrete to flow directly to its intended location. Placement is slow and controlled, with constant monitoring to ensure no voids or weak spots form. Alignment is critical, because even millimeters of deviation can affect the structure above. Engineers constantly measure positioning using sonar, lasers, and GPS systems. Every step requires careful precision, as currents can shift heavy components instantly. Storms halt work, currents shift materials, and visibility can disappear without warning, stretching underwater construction schedules across years. Historical underwater engineering projects illustrate these challenges. The foundations of the Verrazzano Narrows Bridge in New York required workers to excavate and place concrete caissons more than 100 feet below the water's surface. In the Thames Barrier in London, cofferdams and diving systems were combined to create movable floodgates in a tidal river. Each project required engineers to solve unique problems with patience, innovation, and careful planning. In modern projects, underwater sensors monitor structural integrity continuously. Embedded sensors can detect pressure, vibration, and minor shifts, alerting engineers to potential issues before they become problems. This integration of technology ensures safety while allowing work to continue at unprecedented speeds. Even with technology, human oversight remains essential. Engineers decide how to distribute loads, which materials to use, and how to respond instantly to unforeseen changes. Every underwater construction project is a negotiation with nature. Water is unforgiving, unpredictable, and invisible, yet engineers do not fight it blindly, they respect it, study it, and work with it. When completed, the results are invisible to the casual observer. People cross bridges without ever realizing the foundations are built under immense pressure, with workers laboring in total darkness, and concrete placed with millimeter accuracy. Ships pass over massive underwater supports, and tunnels carry traffic without any visible evidence of the complex engineering beneath.
Keep a close eye
The success of underwater construction is measured by invisibility and reliability. It is not about raw strength alone, it is about patience, precision, understanding, and respect for the forces of nature. Every underwater project is a lesson in engineering mastery, showing how humans can conquer extreme conditions while working in harmony with water. Even after decades, the challenges continue. Engineers maintain, inspect, and repair underwater structures regularly. Diving teams revisit old foundations, checking for corrosion, sediment buildup, or cracks. Sensors relay real-time data, and ROVs capture images for engineers to analyze. Modern underwater construction is a combination of human skill, advanced technology, and meticulous planning. Without this combination, the massive bridges, tunnels, and foundations we rely on every day would not exist. Underwater engineering is a silent but vital achievement, unseen by most, yet essential for the modern world. Every project begins with danger and ends with invisible triumph, proving that patience, precision, and respect for nature are the real foundations of human progress. Safety protocols evolve constantly. Engineers document lessons learned from every project. Emergency drills are conducted, decompression schedules are strictly followed, and modern diving systems are tested repeatedly before entering the water. The combination of human skill and technology allows projects that would have been impossible a century ago. Modern bridges, tunnels, and piers are constructed with a precision that protects lives above while hiding the danger below. Every pump, every sheet pile, every measurement matters. Even the smallest misalignment can affect the load distribution above, potentially causing problems years later. Engineers use decades of research, advanced simulations, and meticulous planning to ensure this never happens. Underwater engineering requires an extraordinary understanding of materials, machines, and the human body under pressure. Steel corrodes in saltwater, concrete behaves differently when poured underwater, and currents shift heavy loads unpredictably.
Yes,
Engineers
I see it.
plan for
Rerunning
every
the
possible
diagnostic map.
variable, from tides to seasonal temperature changes, to ensure structures last decades without maintenance failures.
The ascent protocol
Historical
allows for the
examples
depressed
teach
objective.
lessons
Confirming
that
that
modern
alignment is
projects
critical.
refine. Bridges in New York, London, and San Francisco all benefited from previous projects, improving cofferdam and caisson techniques, and integrating modern sensors and robotic systems for monitoring. Ultimately, underwater construction is a testament to human ingenuity and courage. It is unseen work that supports the structures we take for granted every day. Bridges span vast rivers, tunnels carry millions of vehicles, and massive piers hold up enormous buildings, all because engineers learned to negotiate with water.
All systems are nominal.
Every project
Bridge.
demonstrates patience, precision, and respect for nature.
As planned.
The work may be invisible to the public, but it is essential, dangerous, and awe-inspiring. Underwater engineering is not about brute force, it is about intelligence, planning, and the silent mastery of one of Earth's most powerful forces, water itself.